Okay, I'm now going to define the cyclic group of order n. We've got this nice relationship of powers, and we can raise any element of a group to a power n, where n is any integer. So I'm going to require that A is a member of my set G, but now I'm going to also do something, so that tells us that A squared is also a member of G, and so forth. I'm now going to require that A to the power n equals the identity. So if you carry on multiplying by A, you eventually get back to the identity element. So this is a group because effectively we're considering addition modulo n. So let's just have a look at this. I'm going to require that A cubed equals the identity element, and then I'm going to see what happens. So I've got E, which is a member. Of course, that's equal to A to the power 0. I've got A, which is A to the power 1. A squared, which is A to the power 2. And then A cubed is just... A cubed is, of course, just the identity element because I'm requiring that A cubed equals E. So it's like we've got sort of a triangle and we're going round and round and round, but we forget how many times we've gone round the triangle. So let's work out a group table for this. We've got E, A squared, E, A squared. E times anything is just the element, so it's E, A squared, and of course I can do the first column as well by the same logic. A times A is A squared. A times A squared is A cubed, which is the identity. A squared times A is also the identity. A squared times A squared is A to the power 4, which equals A cubed A, of course, which equals EA, which equals A. So there it is. Well, we better check that it's a group. It's closed. Just look at it, it's closed. Because there's nothing in this table here that's not in the modulus. We've got a neutral element, which is of course A to the 0. Have we got an inverse? Well, yes we have. Of course, e to the minus 1 equals e. Why is that? That's because e times e equals e, which is kind of a bit pointless. What about a to the minus 1? Well, a to the minus 1 equals a squared because a times... I guess I could use this little circle as a symbol. I'll maybe put that in there as well. A circle A squared equals A cubed, which equals E. So A combined with A squared equals E. So that tells me that this is the inverse of A, because by definition A minus 1 equals E, and of course we've got A squared there. So that tells me that A minus 1 equals A squared, because these two elements coincide. So that's nice. What about A squared to the minus 1? Well, that's equal to A, of course, because A squared, A equals your identity as well, and so this thing here, because A squared to the minus 1 equals E, we know that these two terms coincide here. Oops. So it's a nice little group. And of course I don't need to specify A cubed equals 0. I could say A to the power anything, 159 equals, sorry, not 0, equals the identity. I can make this as large as I like. So just to link this back to geometry, it's just as though we've got a triangle, and we can, that's the identity, that's A squared, and that, going from there to there, corresponds to multiplying by A, multiplying by A, multiplying by A again. If you do it 3 times, you get back to the identity element. And those of you who know about equations, complex equations, will know that if I specify omega, which is a half minus root 3 over 2I, then omega squared is this thing squared, which turns out to be a half... that's minus a half plus that. That's minus a half minus root 3 over 2I. And omega cubed equals 1. So this system here corresponds to cyclic multiplication of order 3. So that's jolly fun, and I'm going to stop there because I'm getting tired.